Okay guys, so we're going to get started on chapter 2 with a review of domain and range. And in number 1, they're asking you to take those 4 coordinate points and just identify the domain and the range of each. So we know that the domain of any given function is those x values. So I'm just going to go and pull those out of those coordinate points. So I'm pulling out the first coordinate point from each of those pairs. And then we'll go back in and pull out the y values, the second. And you're going to notice that when I do that, they're not in numerical order. So the thing you can do from here, and the thing that you need to do, is actually reorder them. And if there's a number missing, or I'm sorry, a number repeated, only write it one time. So really, the way this needs to look is 1 and then 2, just one time, even though there's 2 of them, that's okay, and then 3 and 4. On 3 through 5, they ask us to use the vertical line test to determine whether the relation is actually a function. So remember, a function can only have one one y value for each x. So we can actually look at our tables. If we had a set of tables with the coordinate points on it, we could look there. But the easiest way to do it is the way they're having us do it right here, which is that vertical line test. And we talked about this in Algebra 1. If you take your pencil and you put it up at the top of the graph and you run it down through the graph itself, it should only hit that function at one spot, only hit that graph, rather, at one spot if it is a function. So this one right here, number 3, only hits it at one spot, so yes, it is a function. Now if we come over here and do that same thing on number 4, we run a line down, we can see that we hit the graph here and we hit the graph there as well. And so because we hit it in 2 spots and not just one, that lets us know that if we were to see these values in a table, there would be they wouldn't match up with the one-to-one like we need, okay, the pairs. So because of that, this is not a function. And then this last one, of course, we're going to run it down, see that it only hits at one point, so this is also a function. Now we're going to get back into graphing on 6 and 7, the linear functions. So remember, linear means that the the exponent on the variable x, here in this case, is 1. So we know we're going to have a straight line. Remember, linear means a straight line. So linear function is always a straight line. And so that's what we're going to be dealing with here. We're dealing with our y equals mx plus b, so our slope-intercept form. And if we take that into account when we see this y equals 3x plus 2, we need to remember that the b is our y-intercept, so that's what that stands for. So in this particular problem, 2 is our y-intercept because this is our b right here. If I write the skeleton for this problem over top, if I write that y equals mx plus b over top, you can see that positive 2 is our y-intercept. So we're going to start there. That's where it crosses the y-axis, is at that 2. And then the coefficient on the x, the m variable, is 3, and that tells us our slope. So I'm going to come down here and just write our slope is 3. It's a whole number, and so because it's a whole number, that means it's over 1. And so that's important because when we go to do our slope, that means that the 3, anything in the numerator. So what we know from this then is that we need to go 3 units up and 3 units to the right. And we know that because the definition of slope is rise over run. So from that y-intercept that we plotted, that's the first thing you do is plot that y-intercept. And then from there, I'm going to go up 3 units, which actually is going to take me off the graph here, but that's okay. Let's just Let's just go with that for a minute. And then I could go over to the right one. So that's going to put me at my new point, which is 1 comma 4 there. Oh, 1 comma 5. Okay, so that's the new point right here. Now, because that graph, you should remember this from Algebra 1, because that we went off the graph there, we can actually go down as well. You can do the opposite of. So we can say, because our slope is 3 over 1, you could also call that negative 3 over negative 1. Okay, because if those two signs, if you cancel those two negative signs out, you really do get a positive 3 in the end. But it's useful for us because that would let us go down 3 and to the left 3. So when we go from 2 down 3, it'll put us right here, and then we'll go to the left 1. And you can see you can get a second point that way. You don't have to do that. In this case, it's just helpful because the point up from the y-intercept was off the graph. All right, and then of course you would connect those dots. So let's go ahead and try number 7. I'm just going to enlarge a little here, and we're going to do the same thing. So if I write the skeleton of this type of equation, this linear equation, over top of that original equation, you can see now that our our y-intercept now is negative 2 instead of positive 2. Okay, so we've got that minus 2. So I'm going to go ahead and plot that. That's our first step, plot that y-intercept. Then we're going to go back and we're going to say, okay, what is our slope? Our slope here is negative 2, and I'm getting that from the coefficient on x, the m value. That's always the slope. I'm going to put it over 1 because it's a whole number, and we need a numerator and a denominator. The numerator will tell us our rise. The denominator is going to tell us our run. So rise is up and down. That's the y-axis. Run is left and right, the x-axis. That negative 2 tells me that negative sign, remember, is a direction, and so that's going to tell me we're going down. The 1 is telling me that we're going to go to the right because it's positive. All right, so the negative sign in the numerator, it tells us the direction up and down. The negative sign in the denominator tells us, the sign in the denominator tells us left or right. Okay, since it's positive, we're going right. So I'm going to start at my y-intercept that I already plotted. I'm going to go down 2 units, and I'm going to go over to the right 1. Now, I can do the same thing to get a third point if I wanted it. If m is negative 2 over 1, I can assign that negative sign to either the numerator or the denominator. It's still negative 2. If we reduce it down, I still have negative 2, an m of negative 2, which is what we want. That's what we started with up here, this m. And so then what I can do, since the numerator tells me direction up or down, that means it's positive in the numerator, so I'm going to go up 2. And I'm going to go in the denominator. Now it's saying negative, so I'm going to go left 1. So I'm going to start with my y-intercept again. Make sure you're always starting with your y-intercept when you're doing these. Now I'm going to go up 2, and I'm going to go to the left 1, and then I will connect the dots on that as well. Okay, now we'll move on then to number 10. In this one, we have the same formula. It's just now our coefficient, our m on x, is 1/2. All right, so that means that my y-intercept, so here's the skeleton, y equals mx plus b. My y-intercept is 2. I'm going to go ahead and plot that. And then now I have it in fraction form, that slope. So, and that's actually means we don't have to put anything over 1. It's already a fraction. It's still rise over run, and they're both positive. So positive in the numerator means I'm going to go up. Positive in the denominator means I'm going to the right. So I'm going to start at my y-intercept. I'm going to go up 1 over 2. There's my second point. Now we can do the same thing here so that we get a third point. We can call, instead of calling it positive 1 over positive 2, we can call it negative 1 over negative 2. It's just another way of saying positive 1/2. It's useful in this scenario because then it's going to let us go down 1 and to the left 2, because that's what it means, down in the numerator, negative in the denominator means go to the left, and then you've got 3 points that you can connect. Okay, now in number 13, We have y equals -1. So we have a y-intercept at -1. Okay, that's our b. What we're missing is the mx. Okay, we're missing the x component to this, the x term. And the reason we're missing it is because it doesn't matter in an equation like this. It doesn't matter what the x is. The y is always going to be -1. So if we kind of move down the number line, when x is 1, y is -1. When x is 2, y is -2. And so on and so forth. We can do that down into the negatives as well. Every time you have an x, you're going to come out of that function with a y of -1. It's kind of a special case situation. So when you have y equals any kind of number, you're going to plot that number. In this case, it was -1 because that's the intercept. And then you're just going to draw a horizontal line through that number. All right, let's do one more. You have a y-intercept of -1. Your slope is -1/4. So we can assign the negative sign to the numerator or the denominator. I'm going to put it in the numerator first, and that means I'm going to go down 1 and to the right 4. So down 1 to the right 4 will put me right here. And then I'm going to do the reverse just to get a third point. I'm going to put the negative sign with the 4 in the denominator. So that's going to tell me to go from my y-intercept, go up 1 and go to the left 4. Remember, I'm always starting at that y-intercept. So I'm going to go up 1 to the left 4. And there's my third point, and then you'll connect them. In 15 and 16, they ask you to tell whether the function is linear and then evaluate it for that given value of x. The only thing they've changed here is they're calling it y, f of x, instead of y. They've just substituted in f of x, and that should probably look a little bit, sound familiar from Algebra 1. They mean the same thing. It's still your dependent variable. It's just that they're using function notation. So they're saying when the function, what is the value of the function when x is a certain value? In this case, number 15, they're saying when x is -2, what is the function of the value of the function? It's just another way of saying what is the y when x is -2. Okay, so it doesn't change a whole lot, but this function is linear because it takes this form right here. Okay, so if it's in y equals mx plus b form, meaning the x has an exponent of 1, and it's sitting there with that b, then it's linear. So the number 15 is linear, whereas number 16 right here is not linear. Okay, this does not follow y equals mx plus b. We have an x squared in here. We have a third term in here that has an exponent of 2. So this one is not linear. Now going back to the second part of their equation, their question, they're asking you to evaluate it at the given value of x. So that means right here they've said, instead of just saying x equals -2, they're putting it in this notation. So what is the value of this function when x is -2? So we're going to find the value of the function when x is -2. So f of x is 3. Okay. Another way to write that, and we'll get into this a little bit later in the book, is that when the x is -2, then that means the value of the function is 3. So you can actually put it all in there together, and that would be the most accurate way to answer this, because you have all that information in the same spot. Then you can get your coordinate point for that function right there from that answer. We'll do the same thing on number 16. Even though it's not linear, it doesn't mean we can't evaluate the function at 1. We can still do that. We're going to say, what is the value of the function when x is 1? All right, and that's just for information on that side. That's just letting you know that we're evaluating at x of 1. Then I'm going to go in and substitute the 1 in for every x up there. So I've got 1 squared plus 1 minus 2. And then that would give me 1 squared is 1, plus 1 is 2. 2 take away 2 is going to give me 0. So the value of the function, when x is 1, the value of the function at x of 1